All right, so randomization in statistics. In data collection, we use random sampling to avoid bias. And that is when the statistic, or bias, when the statistic from your sample over or underestimates the population's parameter. Now, that's not our exact typical definition for bias, but for the sake of this, that's what we're doing.
It's like the stats definition.
Oh, no, there's going to be a different stats definition of bias eventually, but for right now, that's what it, yeah, that's what it pertains to. So that's in data collection, but we're trying to avoid, and we don't know what kind of biases there are yet. That's like chapter 14 or 15 when we learn about bias and what all that looks like. But if we just went to like one neighborhood, for example, we would potentially get bias because of typically, I mean, birds of a feather flock together, right? So.
Does your foot itch or something?
Is it falling asleep?
Stick a pencil in there.
Yeah, I was gonna say that's the best option. Just like shove a pencil up there.
Did you own it?
Or scratch the other ankle, and that will, like, by default, it works.
It cancels out because of
I did that with my arm when my arm was broken.
I feel like
It hurts, Robert.
I feel like it would just make the other one more jealous.
No, it works.
Oh my god.
Make sure it's on the right side of your ankle.
Yeah, it's got to be in the exact spot or it doesn't work.
It cancels out because of the
She said inverse property last time.
Okay,
It's the free-
anyways.
What?
But
What is this?
in an experiment, we use random assignment of subjects to treatments. And so basically randomization allows us to equalize the effects of unknown or uncontrollable sources of variation among treatment groups. All right, so on your paper, I want you to pick a number 1 through 4 and write it down on your paper.
Do you want like whole numbers?
From the list presented,
Gosh.
Whole numbers.
1, 2, 3, or 4.
it's not meant to be complicated. Does everybody have a number written?
Yes.
All right, Nathan, what number did you put?
2,
Peyton,
4.
Josh,
3,
Josh?
1.
Okay, well,
Did that not work out? Supposed to?
no, it's fine.
Wait, how do we do that though?
Normally that doesn't happen.
No,
So
I'm
We're
not
just better.
capping.
So 25% pick 1, 25% pick 2, 25% pick 3, and 25% pick 4. Normally what ends up happening is somebody chooses, like several people choose the same number, and so anyways, but it's obviously random because you were all in your own brains of the number that you wrote down, and so
That's still funny though.
anyways. Alright, example 2. If I were to select a student at random, what does that mean to you?
It's just like
It's just like
just pick out a random name of a student.
So like if I had
it means you didn't get
all 4 of you, that's 2 colors that are similar.
that's probably
So if I had all 4 of you in a stack, and I said, I'm going to select one of you at random, what does that mean to you?
we're just a probability, we're just a percentage.
Okay, so what is your chance of being chosen?
25%.
And does everybody have an equal chance of being chosen?
We should.
Yes.
Yes, okay. Now if I put 2 browns in here, what happens?
It's not equal.
It's not equal anymore, okay? But right now, everyone has an equal chance of being chosen,
Yeah.
okay? So, what this tells us is that we don't know who would be chosen ahead of time. I haven't like already decided in my head that I'm picking Peyton, right? It's going to be completely random when I draw a Sharpie out of my hand that represents one of you. Each student has an equal chance of being selected. Like, did y'all ever have a teacher that had like your number, say when you were in like an elementary school, you know how like you had like a number assigned to you? Like I was always like either number 1 or 2 depending on if there was somebody ahead of me in the alphabet. And then the teachers would have like a popsicle jar of numbers and they would like pull it out. Everybody had an equal chance of being chosen because everybody only had one number in the jar. But that basically is what this is. Randomly selecting you. Alright, so what can go wrong? We don't want to overstate cases. What does that mean? Basically, simulations show what might happen, not what will happen. So just because we said the other day that it would take, 8 candy bars on average to get our 3 game pieces, we shouldn't say that that is what is going to happen. Okay, it could take 100 candy bars. We could possibly never get it unless we had every candy bar in the whole world. I mean, it's, but at minimum we said there had to be 3 because we needed 3 game pieces, right? So it just tells us what is possible to happen, but not a guarantee of what will happen. To model potential outcomes accurately, don't imply outcomes are equally likely unless they are. So when we did that candy example, there was like a 10% chance of choosing blue, a 40% chance of red, and a 50% of white or something like that. Okay, we can't model that they all are equally likely to occur. Like, that we have to make sure we treat it as what it is. Okay, if I put one of you in my stack twice, I can't model this as equally likely for all of you because somebody has a better chance than the others because 2 out of 5 could be chosen instead of 1 out of 4. And then also don't lump together outcomes. Meaning, like, we need to model all potential outcomes. So, like, don't lump the Joshes together and just be like, well, I pulled a Josh. That's not, you know, you're each are your individual person. See, y'all laugh at this, but you're going to remember it.
I will actually, yeah.
Josh square doesn't actually go together.
Correct.
All right, and then run enough trials. So these are all things that could go wrong in the scenarios that are given. So don't make judgments. On a few number of trials. We want to run 20 trials if it's by hand. Okay, meaning using the random number table. Now, if you're using your calculator for the sake of space, it's still going to be 20. But if we are using a computer, it's going to be 100 trials. Because the more trials we have, the more accurate our data is going to be. I think we've got time. We'll go to the next one. Because these are technically separate questions under the one main question. They don't go, like, they don't follow each other. So, explain why each of the following simulations fails to model the real situation properly. So, use random numbers 2 through 12 to represent the sum of two faces when 2 dice are rolled. So, or the sum of the faces when 2 dice are rolled. So, basically, a dice has 6 sides, right? 1 through 6 on each side if it's a fair dice. Okay. And so we're talking about the sum. Okay, so that means if on one dice I rolled a 2 and the other dice I rolled a 6, that sum is to 8, right? But how else can I get a sum of 8 off of 2 dice? 4 and 4, 5 and 3. Okay, there's several options. You can't get a 7. 1 through 6. Okay, there's several ways though that I can get that total, right? And so not all outcomes are equally likely. Because how many ways can I get a sum of 2?
Only 1 and 1.
Yep. So there's only one way I can get that. But 8 I can get, we said, 2 and 6, 3 and 5, 4 and 4. Right, so there's 3 ways I can get that. How many ways can I get 11? 6 and 5. So that's it.
Not 7 and 4.
Yeah, not 7 and 4. Okay, so again, that just goes to show you not all outcomes are equally likely. And so, like we said, for example, a sum of 8 is more likely than a sum of 2. this function. I have to remember where this function is that I'm looking for. I'll get there one day. Why is it not there?
What about your shoes? Hopefully all this stuff is, I don't know, so I better grip them all.
What shoes have you got?
I got.
Oh, I found it.
She already got one.
Well, it came in.
All right, on your calculator, if you hit math and then you arrow over to PRB, which is the probability option, and you go down to number 5, it says RAND INT for random integer. Okay, this is the calculator function for that. And then it's going to ask you, or it's going to give you options. And so we would type in random integer 1, 6, and 2. So that means the numbers 1 through 6, 2 at a time. And there is a comma button above the 7 in case you're trying to figure that out.
That did take me a second.
So it'll look like this once you type it in. So it'll look like that. And so all that says is, I basically told it, I want you to give me 2 random integers from 1 through 6. So this is, I rolled a dice without actually rolling the dice.
Huh.
If you hit it again, I got 1 and 5.
Oh, I got 6.
Hit it again, 6 and 3. So right there, I just did 3 trials with 3 clicks of a button. Right? So all this is telling me is that I'm taking the numbers 1 through 6, 2 at a time. Okay, now there are other ways to do this as well, but that's the one way to get random integers. And so you could have said, I want 3 at a time. And so basically, if we got that, okay, so for me, I had 5 and 4, so the sum is 9. 1 and 5, the sum was 6. 6 and 3, the sum was 9. And so that would be how you can actually, if we were to run the trials on it, but you don't need to worry about that right now. I just wanted you to see this before we move on. But B and C will do a little bit more with it tomorrow, obviously.